Okay, that went. All right, so we're talking about an electric generator. Oh. So remember we had sides 1, 2, 3, and 4. Came up with an easier way to understand this. If we look at if we look at this straight down the center here, on each side, and so then the side you can't see would be like one. The side you can't see, like side 1 would go back into the board, and side 2. Well, you know. Yeah. There. It's sides 2 and not 1 and 2, 2 and 4. Sides 2 and 4. Now, the 1 and 2 comes into play when we say let's call this half of the half of side 1. We'll call this 1, this part side, that half side 2, and then we're going to say our EMF is going to be V cross B times L. VBL. And we also know that each one of these is going to be R. Because you remember the entire length of that side is 2R. Which then makes this VBR. Okay. So if you're looking for the E total, however, on side 1, it's VBL. On side 2, it's negative VBL equals 0. So we get no induced EMF from sides 1 or 3. Because I came up with an easier way to explain it.
This is taking me.
Mm-hmm. You can keep it if you want to. This is just an easier way to understand it.
Yeah.
Yeah, I saw that. I don't.
What's that?
I don't know. What's he supposed to? Yeah, I know. So I can do this. He doesn't like that.
Hey, check it out. See? You're gonna go in, you're gonna flex it. Oh.
But what is this for? No, I grew up with Clippy. Okay, so yeah, I don't know what he's for. Oh.
He's throwing, that's off the page.
Oh, he doesn't. There, he went away. Yeah, that I saw, but still, that just showed up this morning out of nowhere. I was like, what is this? No, I grew up with the nightmare that was Clippy. The original Microsoft Word helper. Uh-huh. Clippy was a nightmare. Now, we need to figure out the EMF from sides 2 and 4. And we need an average, so we need to find an average magnetic force because as it's rotating, theta is always changing. Okay? So what is our magnetic force? Okay? QVB sine of theta. Our average force is then going to become and what is the E? Yeah, the fundamental charge. So the thing is, if we have that average force, our average EMF has to look the same way. However, we have to change this a little bit because we have a rotating system. So if you go back to something like this, you had better not say that. A lot of you guys have very big career aspirations. The one thing you've got to stop doing is learning and erasing. Alpha. On the rooster? Yeah, what is this? It is. It's a rotational kinematic equation. Now, there is no angular acceleration, so that's 0. So what we get is delta theta is going to be omega t. Omega is your angular speed. So omega times t is radians per second. Or omega t is an angular frequency. So now what we're going to have okay, so then our total Yankees not beef. Goose turkey. Did you really just say it? I want you to repeat what you just said real slowly. Yankees a yes. I was like, did you intend to do that? Okay. It's like the time someone on Twitter said, flat earthers from all around the globe are meeting. And someone replied, I want you to repeat what you just said very, very slowly. Now we know the EMF from sides 1 and 3 is 0. So now we need EMF of side 2, EMF of side 4. But why do I change it to this? Mm-hmm. It'll end up going back to plus, but we can't just assume that. So we have the velocity from side two, BL sine of omega t minus V4, BL sine of omega t. V2 is a positive V. And so we end up with 2 V BL sine of omega t. Yes. Let's see. So this generator, if you look, it has sides of 2R and L. So I did something in my notes. I'm not sure. Hang on. Yeah. Where you end up, the equation you need. Oh, that's why. Okay. So and what velocity? Well, so here, so tell me this. You should know this also. Linear velocity in terms of angular velocity and radius is what? Okay, so now we have 2 omega r b l sine of omega t, and we end up with our EMF for this generator as omega BA sine of omega t. Ah, yeah, see, I wrote it there. I just forgot to carry it through. Now, how does this change if I have a loop in my generator with n turns in it? Yeah. Well, what happens if this loop in this generator has n turns in it? N turns. No, n. Yeah. How? Nope, we've done this multiple times. Yep, if you want credit for something that you said, you have to say it. Uh-huh. Yeah. You multiply it in. Because I asked you and you said add in to it. I take it the rage is starting early. Usually the rage follows the sarcasm. Yeah. Oh. Now, for a generator, that's rotating like this, the sides are constantly switching places. You get a signal that looks like this. What kind of, so you get this signal, your sides are constantly changing places in this constant magnetic field. What kind of current is this? Well, it's a sine wave, yeah, but what is this current? What kind? Yep. This is an alternating current. And then, just to add to it, the rate at which electric energy is generated the power generated is going to be your EMF times I. You could, yes. Give it just a few minutes. Okay. A generator produces an EMF of amplitude 18 volts. Amplitude. You have to think about that. When rotating with a frequency of 24 pi radians per second. How will the frequency and amplitude of the EMF change if the frequency of rotation drops to 20 pi radians per second? Do you notice how some of these are rotational frequencies and some of them are standard frequencies? You see, I told you the rage comes after the sarcasm. Let's see what we can do about that. Okay. How does standard frequency connect? What equation connects standard frequency to angular frequency? So frequency is in inverse seconds or hertz. Angular frequency is in radians per second. So if you had to come up with an equation that connected, say your omega to your frequency, what equation is going to do that? How do I get from hertz to radians per second? And how many radians will this generator turn through? Yeah, which is how many radians? 2 pi. So if I have 1 over seconds and I have 2 pi radians, what do I do with them to get radians per second? Yeah, what does that mean? Not atom. Yep. So which means that F is going to be omega over 2 pi. Okay. Now, we need to find out what what these two different frequencies are, okay? So frequency 1, that is going to be your 24 pi radians per second divided by 2 pi radians. That is going to give you 12 hertz as an initial frequency. The second frequency is your 20 pi radians per second over 2 pi, which is going to give you 10 hertz as your second frequency. Now, the amplitude of this EMF is 18 volts. So let's just start with okay. Where is the amplitude? Look at this signal here. Where's the amplitude? Where? It's both up and down. Where? The peaks. Those are your amplitudes. So that is going to be your maximum EMF. There's a number of ways you can look at this. It's your EMF when, since it's a sine function, it could be like when the cross-sectional area of your loop is perpendicular to the magnetic field. But the whole point is your maximum amplitude occurs, or your amplitude, your maximum EMF occurs when your sine function equals 1. So you end up with N omega. It's not 0, it's 1. Your amplitude is is going to be your maximum value. So sine has to equal 1. Remember, your sine functions and cosine functions are going to oscillate between +1 and -1. Your amplitude, your maximum value occurs at either 1. Yeah, it occurs at 1. So we want to figure out that second EMF. We can say, well, E2 over E1. We already know as the rotation drops, we go from 12 hertz to 10 hertz as our frequency. Now we can say we have N omega 2, dA over N omega 1, dA. Omega 2 over omega 1. Our E2 is going to be omega 2 over omega 1 times E1, 20 pi over 24 pi. Your E1 is 18 volts. So your second EMF, as the rotation drops to 15 volts. Change them to what? Because you also needed to know how the frequency changes. EMF change and frequency change. Faraday's law. What is phi? What does that mean? We did it with phi E. What is phi B? It's what? Yeah, magnetic field. What does phi usually mean? Yes, it does. Yeah, that's what it is. I know. Sound it out. You guys will be fine. Now, first thing you need to keep in mind is you're going to have a new unit. Oh, and I think I spelled it wrong. It's supposed to be just 1B. So your unit now is WB. Those are Webers. And that's 1 Tesla times square meters. Okay, so let's kind of think about this. What might this look like? I'm not going to give you the easy, like perpendicular situation. What do you think this is?
I do know.
Nope. And that's some area A. It's your magnetic field. So very carefully. There's your perpendicular component. It's your B cosine theta. In this case, that's your theta. And then, of course, your area vector. So that's where we get the flux. So mm, I guess it makes more sense if we just don't put that in there because it's the magnetic field perpendicular to the surface. I don't want you seeing those two vectors and thinking, but those are parallel. You could draw that vector in and say it's also B of A perpendicular. It's same idea. Now we're going to need we are going to need an EMF in terms of magnetic flux. Okay, so let's remember what electric flux looked like. So what do you think magnetic flux is going to look like? Yep, surface integral. Do what? Yep. Now we already know. So what we can extrapolate to and let's see, and at theta equals 90 degrees. Because what happens to the cross product at 90 degrees? So what is the cross product like? B cross B becomes what? B what? So at 90 degrees, that just becomes V times B. We're going to get VBDL. B and B are constants. Then we have to ask ourselves what DL is. And that's bad. Supposed to be kind of looking at a circle on its side. Now, granted, this is larger than it should be, but here you have your DL. If that's DL, what's in here? And so your DL is going to be R d theta, and that's the arc length formula. So now we're going to have B, and that path being a circle goes from 0 to what? 2 pi. Well, we know we can pull R straight out because it's now a constant. which 2 pi r is going to give us a circumference. So in a general term, that's going to come out to be the length of the entire path. Now what we want to do is first we're going to look at kinematics. And let's kind of remember our path here. So let's say one of these sides is a length of L, one of these is a length of W. We kept off the acceleration term. We know that we can take deltas and reduce them down to an infinitely small differential. And so we'll start by saying area is length times width, which for us is going to be length times delta x. So now we have a dA element, L dx, which is going to be LV dt. Okay, so if we go back to our what we're going to do now is differentiate. That's just going to get rid of the integral. BLV dt. So now we're going to get, we're just going to divide through by the dt. So we have d by b equals BLV dt. We're going to get d phi dt equals BLV. We already said BLV equals what? Mm-hmm. So that means and one thing that you're going to find is the current induced by a magnetic field produces a magnetic field that counters the flux. So you have flux going that way. The current that's induced in the wire, whatever you have, is going to go in such a way that if your flux is going this way, you're going to produce a magnetic field going that way to counter the flux. So you change this to and then for you guys solving problems, it becomes so we have a discrete version. And for a coil with n number of turns, and this is Faraday's law. So again, the conceptual is, imagine you have a circular wire. And you have magnetic field fluxing through it. Magnetic field's fluxing, like, let's just say it's fluxing that way. It's going to produce a current in the wire that produces a magnetic field that goes that way to resist the flux. So then you should be able to use the right hand rule to figure out which way that current goes. So if there's flux going that way, I have to have a magnetic field going this way, so it has to wrap like this. That means current has to be going this way. All righty. So let's see, you have a magnetic field between the poles of a magnet, has a magnitude of 0.55 Tesla. Circular loop of a wire with radius 3.2 centimeters is placed between the poles, so the field makes an angle of 22 degrees with the plane of the loop. What is the flux through the loop? Okay, so let's give ourselves a loop. What the heck? No. Okay, so I'm going to put an axis through here, because then I want to say that I have a magnetic field fluxing through at 22 degrees. But I know that my flux is B dot A. And I know that my vector A is there. Well, so if I move it over, same idea. So the angle that I really want is phi. Yeah, so your A vector, you can put the A vector anywhere. It's just going to come perpendicular off of the area of that circle. But you notice that the magnetic field forms a 22-degree angle with that circle. So you're really interested in phi because you want the angle between the area vector and the magnetic field. So theta? Yeah, they're both theta. So this means you're going to have 90 minus 22 is 68 degrees. Okay, so your flux BA cosine of phi equals B pi r squared cosine of phi. Why did I do pi r squared? Yep, no, area of a circular loop. Okay, so the flux is going to be 0.55 Tesla. Let's see, pi, your radius is 0.032 meters squared. Cosine of 68 degrees, and you end up with 6.6 10 to the negative fourth Webers. Okay, we'll finish this up, I guess, next Wednesday. And then we'll be starting optics.